So with this question, we are being asked to, it says that a pole stands 75 feet tall. An angle is formed when wires of various length x are attached from the ground to the top of the pole as shown in the following figure. And then we're supposed to find the rate of change for d theta dx when or if x is equal to 90. And I really want to do this question just so that you can see an application of these inverse trig functions. So the situation here is that x is changing. So at the very end, after we differentiate, we can plug in x is equal to 90, but we can't plug in x is equal to 90 quite yet because it's going to be changing and it's not going to be 90 the entire time. So here is the idea of this, is that when you look, you need to find an equation involving theta. And so if you think about trying to write up an equation involving theta, theta is equal to something, we look at the given sides that we have, and we have our opposite of theta, and we also have our hypotenuse. So the trig function that relates opposite and hypotenuse, of course, is our sine theta. So we could write from this figure that sine theta is equal to 75 over x. Now, we're not interested in sine theta. We are interested in theta. So we need to get this theta by itself, and the way we do that is by taking the inverse trig function of both sides. So I would take sine inverse of the left-hand side and then sine inverse of the right-hand side. So then the signs cancel out, so to speak, over on the left-hand side. So we get theta is equal to sine inverse of 75 over x. And then that is the function that we are going to differentiate. So once we get our function of theta is equal to, then we're going to take our derivative. Now, keep in mind that the derivative for sine inverse is 1 over the square root of 1 minus x squared, if it was just sine inverse of x. So our first step for the derivative of the outer is going to be to replace the x with our inner function, which is this quantity in parentheses here. So taking the derivative, theta is going to become d theta dx equals, over here we're going to use the derivative of the outer as 1 over the square root of 1 minus, and then our x's are going to get replaced with the inner, which is 75 over x. So this will be 75 over x quantity squared. Then we multiply that. So again, this function right here, this, so to speak, is our derivative of our outer. And then we multiply that by the derivative of our inner. And if you think about taking the derivative of the inner, you would want to rewrite the 75 over x as 75x to the negative 1. So we bring down the negative. We have negative 75x to the negative 2. All right, so I just want to talk a little bit about simplifying here because, sometimes you're interested in a particular value, but other times you'll need to simplify this. So we have 1 over the square root of 1 minus. Now, the 75 squared is our 5,625 over x squared. Now, we have a denominator here that could be written as x to the second power in the denominator from the x to the negative 2, and then the negative 75 could be in the numerator. Now, there is some simplification that you can do inside of this radical because, again, you would want to get a common denominator of x squared over x squared. So that would be looking like, when I flip this fraction, I would have 1 over 1, and then this flip of this denominator would give us the square root of x squared over x squared minus 5,625. Okay, so that's the whole flip of the denominator because I have 1 over 1 over another fraction. So I could flip that denominator times negative 75 over x squared. Now, I want to bring one thing to your attention here, is that the square root of x squared over x squared minus the 5,625, you can split that up into the square root of x squared over the square root of x squared minus 5,625 times negative 75 over x squared. And what that buys you is the square root of x squared. This simplifies to just x, and you could put absolute values around that, but remember that our x value here is a length, so x will always be positive. So it's not necessary to put the absolute values around the x. Now, what that gives us is that we now have an x divided by x squared. So this x will cross out with this x squared, leaving just one x in the denominator times this radical. So here is what we are looking at for our d theta dx. All of this has simplified out to be negative 75 over x times the square root of x squared minus 5,625. Now, they have specifically asked us to find this rate of change when x is equal to 90. So your last step is that you would plug in 90 into this, and when you do that, again, you're going to have the negative 75 over 90 times 90 squared, square root of 90 squared minus 5,625, and that should give you approximately equal to negative 0.01675. And that is our d theta evaluated at x is equal to 90. Now, I do want to mention we want to write some sort of unit on this, and that's where this d theta dx notation is really helpful, because the unit on our theta would be radians. So this would be radians over the unit on our x. X was a length, and they said that that length was measured in feet. So this would be radians over feet. So another way of saying this is you could say that it is changing at negative 0.01675, so it's decreasing at this radians per foot. Okay, so again, this question is just a really nice example of where these inverse trig functions would come up and how you would need to differentiate them.